all you do is just go through the opening set and then people so they play or whatever. Yeah, so more than not actually no, not really. Because we use like files and stuff like that, which kind of take into account due to like workings. You just plug that here, we can just do like but it's actually taking into account the order.
No, I'm just looking for that now.
There's one right behind me. There might be one over there.
I was thinking like apparently this is like courses based on
Somewhat less.
It's actually really nice I think it's so I think we are we shouldn't basically going so they'll go with the way so we'll go to they found that like slide down actually works.
We're basically just like repeating distances.
I don't remember all
I do better. Yeah, it's actually
so you want to know Oh, the last part you're talking about when you actually try different things. As long as you're between 0.8 on C5.
Yeah.
Awesome.
Okay. Almost exactly the same.
Okay, sorry to be late.
Yeah,
Traffic was quite bad. How's everybody doing? Almost there on the homework?
Almost break time, right?
That's right. Almost break time. Would people prefer to have the next homework assignment be available over the break, or
Yes.
not have it be available?
Yes.
You want to? Okay. I will. I'll post it. What's that?
If anyone says no.
You got a diplomat over there for the case we're having it. Some people don't want to have it there because they don't want to feel like they have to work it over the break. So
10 minutes around that.
I know, but some people can't stop themselves. They're addicted to homework. Okay, I'll post it. Good. Any questions? Yeah.
So last week you were talking about your solutions for recursion for your IO competition, and basically how all of them were PyTorch, having used TensorFlow and used PyTorch. I'm just struggling to understand why PyTorch is becoming the most prevalent library.
There's probably a lot of reasons for that. Probably the main one is that TensorFlow is kind of a pain to use if you have not spent the time to understand what TensorFlow is, what problem TensorFlow is trying to solve. PyTorch solves the same problem in a very different way that feels a lot more like Pythonic, like you're using Python, like you would use it for anything else. One of the main reasons being that the difference. So there's computational graphs in each one. We learned about computational graphs. TensorFlow has a static computational graph, which means that the whole graph, the computation from input to output, from the data input through all the way through the loss calculation, has to be defined and understood beforehand. This makes things like conditional statements very hard to put into your graph because they depend on the state of what's going on. So there are ways of doing conditionals. It's not like it's impossible, but it just is. It feels unnatural, especially to people who are just coming into it and not having had to be having been forced to learn TensorFlow because that was the main and only thing to use. PyTorch has a dynamic graph, meaning basically every iteration the graph is being recompiled, so that you can write imperative Python code conditionals, and those will be executed as they look like, as you'd expect them to be executed in like a standard kind of way. TensorFlow has a much more mature API and has a much better developed story around inference and serving training models. Static graphs are a benefit in that case, but for most people just kind of getting into it now, PyTorch feels easier, feels more natural, and now the ecosystem and the API are really catching up. And one of the benefits of most people using it is that there's now a whole host of, or a lot of people using it now. There's a whole host of tools and libraries built up around PyTorch that are really cool and really make training, getting going on training something kind of, I wouldn't say standard, but like something that's out there, like any of the models that we talked about, really, really easy and fast. And so it's a favorite of cat because that's kind of what you want to do. You want to go into a competition really quickly, train a really high capacity complex model, maybe with a couple different heads, and be able to do that really fast, and prototype that, train it really fast, see how well you're going to do, judge whether you're going to spend all your time on this competition or not, and and move forward. It's just a nice story.
What are some of those libraries?
So Ignite is one that's provided by PyTorch. Catalyst is another provided, maintained by somebody else. Albumentations is another one for doing data augmentation, and just the PyTorch tool. Right? I can put links to that in our page, on Canvas if that feels useful.
Yeah.
But they're very cool. They make prototyping very cool and easy. Yeah. And so it kind of feels like fun. I think TensorFlow doesn't feel fun. Anybody, you use TensorFlow all the time.
Yes.
Does it feel fun?
Now, yes. Beginning, definitely no.
Yeah. I still think TensorFlow doesn't feel fun. There's just something about using TensorFlow that feels like you're using something old, even though it's very new. Okay, let's get going. All right, so we're just going to continue with this object detection and segmentation, and look at a couple different types of models, and also think about depth, like 3D object detection, and just kind of mention the models that are out there. This is not exhaustive, like anything we've done is not exhaustive, but just trying to give you a feel for what exists out there, what models have shown success, for solving certain kinds of problems. Right, so this is what we did last time. RCNN, kind of funky, fast RCNN, sort of put everything in. You put a lot more into the model, so that was almost all end-to-end, although you still have to do these region of interest proposals outside of the network. And faster RCNN actually has a region proposal network that's learned, so it's all in the network. And then we had, this gave us massive speed up, especially at inference time. And then we had some variants on this, like mask RCNN, which allows you to do cool things like this, this kind of semantic segmentation. So, what are some other things you can do with these kinds of models? So, how about labeling, how about producing a sort of paraphrase or some phrase around what you're seeing in the in each of the bounding boxes. So not just that there's a person there, but maybe something more semantic about that. Like in this example, you can see all kinds of not just man or person or even man or woman, but you have man sitting on a table. I don't know that that's quite right, but maybe it does kind of look like that. Or a man wearing blue jeans, or a woman wearing a black shirt, chairs brown. This seems like a pretty hard but interesting thing to try to be able to do. So, how's this done? Well, I think I have a second actually, but first of all, you need what to do anything to even approach a problem like this? Yeah, you need data. You need somebody to go through and label all this kind of stuff. So, graduate students again. Or people you pay nothing on Amazon, Mechanical Turk. You ever had to do any kind of current labeling as a graduate student?
No.
Okay.
No, I would refuse.
Okay. So here is a model for doing this. This is from 2016. So maybe a little bit old, maybe like, there's probably lots of variants on this right now, but this follows much of what we saw in the RCNN category of models. This just adds the additional bit of the labeling. So what you have is like what we had before. You take your image, you forward it through some pre-trained CNN. You're going to get out these convolutional feature map. You're going to get out a convolutional feature map, and then you have this bit of it right here, which is basically what we saw before, which is doing region proposals. This one has a little bit of a different flavor to it, where it's doing some sampling to a fixed set of actual proposals. That's a hyperparameter, but DID is doing the whole ROI pooling that gets you to so B regions, region proposals of size 512 has a number of channels, and 7 by 7, and that 7 by 7. Remember, we draw that grid, and this is doing this sort of bilinear kind of interpolation between like drawing the grid and what's in the grid, like the actual image there. Because remember, when we do these proposed regions, they can be of all different kinds of shapes and sizes. They're not all the same fixed size. But the point of going to drawing the 7 by 7 grid is to give you at the output something that's of a fixed size, so that the next part of the network knows what to expect, like what size to expect. So once you have that, then you have a couple different heads here. One will be to just like before, where you train the region proposal network and train to learn like the bounding boxes, and then to do the classification of what's in there in each of the bounding boxes. But then you also have this part of the network, this other head this has a couple of fully connected networks. This gets you to, so for each one of these regions of interest, the pooled regions of interest, you're going to get some sort of vector output for that. And then they add just one more piece to this. They have a recurrent neural network, which we have not talked about in depth yet, but we will a couple weeks after we get back from the break. This is a particular kind of recurrent neural network called an LSTM, long short-term memory. They feed that in, and that's supervised by the labeled data. So someone's gone through and said, in this green box, there's a striped gray cat, and then in this blue box, there are cats watching TV. So this LSTM is a kind of model that allows you to learn sequential data. And so you now add this head, and you do this captioning. You learn how to output that particular caption associated with your training data, and now you give it your data in your test set, some held out data, and you see how well it did, and you get the models that you were just kind of looking at. So this is another look at this. So let's see how well this did. Let's just start here in the center. So this thing knows a lot about food. So this gets this cup of coffee right. It thinks this bottle of syrup's a glass of water. Not bad. I don't know why it thinks it's water. That's pretty gross water. A blue bowl with red sauce. That's not too bad, right? It's a pizza in a blue bowl. Seems reasonable. A slice of meat, like this burger kind of thing, but it's not really a slice, but there's some meat in there. Yellow and white cheese. Can't tell if that's supposed to be like, I guess those are scrambled eggs, but anyways. Something about an orange, you can't read it. A bowl of chocolates, not quite right. Those are like the jellies and things like that, the butter. But you know, it's like pretty good, right? And really, the reason why these are sort of wrong is that the data it's trained on just doesn't have enough examples to like learn about syrup, maple syrup in bottles, you know. It's really just a limit of the data, not really a limit of the model. Yeah, so blue sign with a white arrow, that's pretty good. White lines on the road, yeah, that's pretty good. A silver car parked on the street, yep, a green traffic light, so that's looking pretty good. Red brick building with window, yeah. So, you know, probably lots of good examples of these kinds of things in the training set. And then, yeah, you got something over here. Paved sidewalk, brown horse with white mane. That's pretty specific, right? White horse, I think it says white horse with white mane. It's off the picture there, but yeah. So that's pretty cool, actually. Right? I mean, I think this is pretty amazing. What it's learned to do is write like a legitimate like phrase, you know, it's a caption, some phrase of English that does a pretty good job of saying what's in there. So, and again, it's not just like it's looking up like some existing caption. It's actually producing the caption, you know, as part of this whole neural network. Again, we're going to get more into how you learn to produce things like language again after the break. But here we are just going to show you this. And again, it's it's building on this idea of the RCNN type models. So there's basically like a faster RCNN here, but then it has this additional piece of being able to train these captions. So cool use. The data here. So there's just this is the data that those examples were trained on. This is something produced by created by Microsoft, and it's actually in partnership with like a couple other groups, including Facebook. But it is COCO. So COCO is common objects in context. Common objects in context. So it's got like a bunch of different sets. Well, it's got all these kind of natural pictures again that are scraped from something like Flickr or something like that. And I guess back before that wasn't a big deal. It seemed like that would be a big deal now. But anyways, it scraped all these things that someone goes through and labels. So sometimes they have like the semantic segmentation type of labels. Sometimes they have like the pose estimation labels. Sometimes they have the captioning, like the bounding box for captioning. It's got a bunch of different subsets. And yeah, so here's, there's all these statistics about it. So 330,000 images, but 1.5 million object instances. So there's, many objects per image. So very different from ImageNet, at least the subset.
Something they calculated using their...
No, well, it's all labeled, right? Like humans labeled it. So it's a lot. That's why there's graduate students for that kind of thing. I mean, the way this is done, right, is like literally like they recruited I don't know how many thousands of people to take subsets of these things and to do this labeling, like by hand. So, so there's two. We've said this a couple times before, but there's really two reasons why deep learning has become a thing. One is GPUs came along and people figured out how to use GPUs to train neural networks, right? Because CPUs were just too slow. You never could train anything big. It just wasn't enough compute for that. So that's one reason, because the computational abilities came along. And the other was that people started to actually spend the time and money to put together significant, like very large labeled data sets to prove these things on. So, yeah. And so anyways, this is one of the main ones. So ImageNet's, of course, one of the big natural scene, or important large natural scene data sets, and this is, one of the other ones. So yeah, very cool. Very cool that they would do that, and also very cool that they would share it openly, right? Like no one has to pay to use Cocoa. Although there's probably some sort of patent somewhere. Kara probably knows the history of that and related issues, but you know these companies. You know, who knows exactly why? I mean, there's like lots of good reasons for it, but all this stuff has been, you know, open sourced and made available for researchers everywhere, which also makes it so that this field is pushed along really fast. There are other kinds of data sets that you might run across, depending on what it is you're trying to do. So this is a data set called Visual Genome, and the way that its data is organized is, again, you have bounding boxes, but you have this kind of relational graph of like things, you know, so like nouns and relationships between nouns, right? So you have there's a notion of a person, and you know, lots of these things, like lots of these bounding boxes have people in them. Some of these have a guitar, and then there's some relationship that's playing. So person playing guitar, and this kind of relationship is associated with the whole image. There's also adjectives like what kind of guitar, it's an electric guitar, what kind of album, it's apparently an Adele album. This is her second cameo in this class. We love Adele, I guess. So anyways, so just like a different set of label, different kind of label. So what can you do with this? Well, of course you can just go and learn, right? So what do you do with this kind of data? Well, you again use these similar kinds of models, and you learn the bounding boxes, and then you learn the relationships amongst the bounding boxes, right? So the bounding boxes give you like the hat nodes in that relational graph. Or sorry, what am I saying? The hat nodes, look at this, like the nouns in the relational graph. And then the label, you know, the training data has relationships between them for this image. So you can learn that the mountain's behind the horse, the man's riding the horse. Actually looks like a woman to me, I don't know, can't tell. Man's wearing the hat, man's wearing the shirt, that kind of thing. And you can just go ahead and learn these relationships, and then, you know, for some reason you needed to have that kind of relationship. This is a data set that you can learn from, and now you can go create your multi-million-dollar startup with this data set. Something like that. Cool, all right, so neat uses of those kinds of models. All right, so now let's go to 3D object detection. So this is slightly harder because there's more parameters to learn. Yeah?
So before we get into this, are people like ever concerned about like the quality of those labels? I mean, 1.8 million, like people are probably, you know,
yeah. I mean, certainly people are concerned about it, and you know, when it's created in a way as like to be kind of like error correcting, right? So it's like you don't just have one person label an image and then just accept that as the label. You have multiple people label it, and then if there's consensus, then you have greater confidence that those labels are right. If there's not consensus, then that gives you an opportunity to kind of go have an arbiter look and see like which one's right, which one's wrong, right? So they are created already with like training, with high confidence being a goal for the labels. But it's also the case that like, you know, when it first comes out, then there are corrections to it, and then the data set gets updated. Yeah.
Can you go to the last slide?
This one.
Yeah, this one. How do they do the scene graph generation? I mean, you can detect the object, and then how can you find the relationship between first object and another object?
Yeah, so this is just another part of the network that takes like pairs of objects and learns the relation. It's like a classification problem, right? So you have all the possible relationships, and you take this pair and you learn that this pair, mountain, horse, like mountain is behind horse. I guess that's like a usual relationship that you'd have for an image, right?
So
You could have mounted in front of the horse, but you probably won't see the horse.
okay, so that relationship is also learned by another interface.
Yep, that's right. Yeah, it's definitely an extension of what we've seen, and I'm not going into the details there, but yeah, that's how it's done. Okay, so we have a few more parameters here. Not only do we have a third parameter of depth for these, but we have to think of how these bounding boxes kind of are oriented in the space. So we only ever have 2D images ever. Like that's just what we do. There's a notion of like depth, and we're going to get to that in a few more slides. You know, like tools like the Xbox Connect have like a depth mapping, that kind of thing. But you know, for the most part, we have these 2D images that are obviously pictures of like things out in the real three-dimensional world. So how do you think about this as someone approaching this problem? And kind of like the toy, or not really toy, but like the heuristic or like the mental model to have is to just remember that your camera. So there's stuff out in the real world, in the 3D world. Your camera is sort of is related to it in some way. It's pointing at this scene in some way, and it has its own point of view, and that defines what's some. I don't even know where this word comes from. Maybe someone who speaks Latin or whatever could tell us like the roots of this. But you have what's known as the viewing frustrum. So this is like the field of view for the camera, and we get some sort of like slice out of that frustrum as the 2D input, or as the 2D like recording of that. Okay, so we use this mental model. So every point in 2D really represents like some ray in 3D, right? And we're just seeing. We don't see the ray at all. We just get, given the orientation of the camera, we just see the 2D evidence of it. Just that point. And there's a whole bunch of these, obviously, all throughout the frustrum. Right. So a 2D bounding box of an image projects using these rays to like 3D frustrum. Okay, so what's the problem with that? Well, there are technically that whatever is creating that like pixel on your 2D image could be at varying distances from the camera, and but then they'd have to proportionally like change in their dimensions to map back to that one point. So there's ambiguity in the scale and distance from that point that we won't ever be able to disambiguate. It's just a problem in these. So again, the object can be anywhere in this camera viewing frustrum. So it's just it's just a thing that we do. Like intuitively, you already knew this, but we give it all fancy names now. Impress the people you talk with about frustrums. Okay, so knowing that, now we go. The real thing here is that someone's still got to go and label all these things. So so when we're doing bounding boxes, we were literally thinking about boxes that were parallel to like the sides of the image. And that we needed 4 parameters to parameterize that. So we needed a corner and a width and a height. So extending that in 3D object detection, we now have our corner has 3 coordinates, and we have 3 dimensions: width, height, and length, shown here in this picture. And we had. This was true also with the bounding boxes, but we could have any like sailors out there who like sees roll, pitch, and yaw, like I know exactly what that is. Anyways, they're just ways of talking about angles of rotation around the 3 dimensions you're in. And so you could literally have now 3 more parameters. You could have had 2 more parameters in the 2D bounding box, but you'd have 3 more here to describe, that this box is like rotated this much around the y-axis, this much around the x-axis, this much around the z-axis. But we're not going to deal with that. We're just going to have no roll and pitch. We're going to allow there to be, that's like fixing the width and height like we did in the 2D, and we'll allow there to be some rotation around the yaw. So like it's always going to be like there's going to be some sort of plane here that determined by the image that all of our 3D bounding boxes will be parallel with, but we'll allow it to rotate around that z-axis. So it's a harder problem because you have more parameters that you have to learn, right? Okay, how do you do this? Well, you just take what worked in 2D and you just expand it to learn all the rest of your parameters. So, a very straightforward way of doing this is to you have now, let's see, 7 parameters to learn, and that's what you do. So you're, everywhere that there used to be a regression problem on those 4 parameters, now there's a regression problem on those 7 parameters. Your region proposing network now has to propose 3D bounding boxes, but that's okay because that's what your data has in it anyways. So you're just training it you're supervising it by exactly those parameters. So you so like in this is actually like really, really simple. This particular example, we have been talking, it'll be like the next slide. But this one in particular was, if you're in 3D, just project to a 2D, just run straight through faster RC and be done. But then you can see how you can extend it. So extending it looks, I guess it didn't have that slide. Weird. Okay. Anyways, maybe you can see you might not extend it. But it turns out that where this is used a lot in practice is in self-driving cars, autonomous vehicles, and there you don't just have a camera that's looking out on the world and trying to drive from that. You actually have other sensors, and in particular you have this LiDAR sensor, which I don't know a ton about, but it basically rotates on the top of the car and it produces data that looks like this. So it's some mapping. So it's like a scatter. Trying to come up with here. It's basically trying to produce depth maps of the environment around you, and the depth is created by sending out signals and then receiving the return signal and then inferring from that. So there's a word for that. Scatter something. I can't even know. Anyways, so you do have cameras. So you have this kind of 2D look on the world, but you actually also get a 3D set of data, which, as you can imagine, is probably really important to have because you need to know something about that. You can't just have this ambiguity of maybe that's a really, that person's not that close to me. Maybe there's just a really, really tall person right here, and then you hit the person, and that's that. Was someone saying something? No. Okay. So what do you do when you have these additional data sets? Well, you just put them all into one big faster RCNN. So a typical self-driving car, autonomous vehicle will have a camera projected out in front, but it'll also have LiDAR that is generating data out towards the front on the sides of the car, and it also has there's LiDAR instruments along the front of the car, and there's also one on the top. and it's giving you these different views. So it doesn't really matter what they are. You just take, you get some labeled data again. So again, somebody's got to sit down and label all this stuff, and you input them all. So you have a proposal network for each of the different modes of data, and you do ROI pooling for all of those. You can have some sort of dependencies from one to the other. So like it makes sense that you might use the 3D information to help in the proposal of your 2D regions, because there's like more information in 3D than there's in 2D. So that will get like scales right and better. And then you bring all these things together, you concatenate them, you learn a bunch of fully connected layers, and then you do your bounding box regression and your classification of what's in the regions. So it literally is this, right? There's not, there's probably lots of variants on this for people who actually are doing this and trying to do the very best they can in this, but these are the kinds of models used. It's these faster RCNN types for all the modes and just joining the modes and making the predictions. And again, this is like what makes neural networks so useful, at least I think, and that is they really are like Lego pieces that you can put together, right? They just, wherever, these were all just vectors at some point or tensors, and now I just kind of concatenate them and treat them all as useful information to do the problem that I care about, so that I actually have the most accurate, detection of parked cars and human beings, walking in the street, and distances from nearby cars, and marking of like the lines in the road, whatever else, whatever else you need. It's all there. So that's pretty awesome, actually. Just take your Legos, put them all together, build a self-driving car. It's that simple.
So instead of convolution layers, could this essentially be like a fully connected neural net feeding into fully connected neural net, or like a fully connected neural net producing class scores?
You mean like from the LiDAR data? Is that what you're trying to say? You always have the option to have fully connected networks, but remember that this input data is enormous, right? Especially, as you add dimensions like depth, like this is huge. So a fully connected network from that will have, like in the first fully connected layer, will have so many parameters. So this is why we do convolutions, is to reduce the number of parameters, but preserve the capacity of the network by, the convolutions learn spatial statistical patterns, and they learn those in a hierarchy. And by doing that, these are still huge models. They have lots of parameters, but they're orders of magnitude smaller than if you were doing fully connected layers. Yeah.
Every time you have images, you don't want to use fully connected layers, because the main thing, as Bergen was saying, is that if you're using convolution, like 2D convolutions, you're assuming that the value of each pixel is related to the value of the adjacent pixels. If you use fully connected layers, then you are removing this assumption, and the network has to spend time learning that on its own.
Yeah, remember too, another benefit of the convolution is that you learn a spatial pattern that is like translation invariant, right? It can be anywhere in the image. And if you do fully connected layers, then you're asking the network to learn it in all, like that pattern in all of the locations of the image, right? So it's another benefit you get out of that.
So this is a good example of why using max pooling or striding helps reduce the space, right?
It does help reduce the space, but I'm not sure how you're getting it to.
It just makes the number of pixels that are going into the.
Yeah, right. So like you have less parameters the next time. Yeah, exactly. Yeah. Good. Good. Okay. All right. Yeah. So like this could either be the input data that you're training on, or this could be the in this case, this is actually like the inference. So it's kind of cool to see this, right? This is what the camera sees at the front of the car, and this is that 3D map from the top, the LiDAR sensor at the top of the car. And they've worked together to produce these bounding boxes, like literally in 3D here, because this has got depth information, and then these kind of inferred ones here. And so now this car knows where all the other cars are on the street, and that is used as input to like not hit them. Yeah, so like that's another thing to remember about autonomous cars, I guess, is like once you've done this piece, you're not done. There's now another learning algorithm that's actually learning how to drive without hitting these things, right? So it's a harder problem, but you need this piece first, and that's done with reinforcement learning, and we'll get to that at the end of the course. Okay. Maybe you don't have a LiDAR sensor at your house that you can collect that 3D data with. Maybe you carry one on your head, you collect the 3D data everywhere you go. But turns out that there's actually like decent consumer devices for getting depth information. And one of which is the Kinect, which I actually don't think the Kinect is sold anymore. Yeah. Which is, I guess, I don't know, this just means that people don't want to stand in front of their video games. They just want to sit and do this. But it's actually a very cool research device. I've used this in research at a healthcare company I worked for, a healthcare research company. And yeah, it actually is doing depth inference. And you can kind of see that here. So here's your RGB image, but then this thing was a heat map. So like the red is farther away, blue is closer, and yeah, it produces this kind of data. So how is this kind of stuff done? So yeah, so like in this picture right here, this is sort of like a slice of depth. So it's not perfect. It's interesting. This is like one of the most interesting kinds of examples, I think, to see like the difference between machine learning and humans. Like we look at a picture like this, and like we are really, really good at telling what is closer, what's farther. I mean, there's definitely like ways of doing optical illusions where you can trick yourself, but generally, if these are like following the paths of the standard like everyday life kind of thing, like we are really good at like. I promise you, all of you can come up here and be like, I know, this cup is closer than this robot thing, and it's closer than this panda, is closer than this like Kleenex box. This looks like it's out in front of the panda, mainly because there's like a little bit of overlap right there. And I also just know that like when people set up their desks, the monitor kind of stands forward a little bit, and pandas are behind it, or whatever your little trinkets are, And we're really good at this, and computers are pretty good at this. So again, this is the part of the image or this is a part of the image that the model thinks is all at the same depth. It's not totally accurate, but it's also not awful. So how to think about these things. So one way to think about this is to voxelize. I'm sure that's a verb. So that so for your image, you actually have a 3D coordinate and the color at that coordinate. And one way to do this is to take your device, capture the depth and the color there, and then partition the space up into these regular 3D grids. So so these are just all kind of localized points that we think are all these are all roughly at the same depth. And if you move to a different voxel, that's possibly that's at a different depth than a voxel nearby it. Or I shouldn't say just depth. I mean, it could be it's different in any one of the three dimensions. And then we fill that with a color. And so this is like a very coarse way of thinking of 3D data for an image. And this is basically what the like something like the Connect returns to you. And so yeah, so how do you draw bounding boxes in this arena? Well, you have these voxelized point clouds. And again, I don't know if I did a good job here of saying this, but like they're voxelized because already the camera has like a lot of uncertainty about how far away it is. So it's got like, you can think of like the box is expressing, like the size of the box is expressing some kind of uncertainty around like how far away it is, or like, and it's not just how far away, it's like where it is in three-dimensional space. But, you know, if you want to draw bounding boxes around these things, no big deal. Feed this into a faster RCNN. The region proposals now just have to match the data that you have. So if you have 6 points of data to infer, which is something about like the voxels, including the depth, and maybe some sort of orientation parameters, then you just feed those things in. So you have your region proposal network. You propose the regions. You learn your bounding boxes and the objects that are in there, and it's exactly the same story. So again, the point that we're making here is like the faster RCNN or all the RCNN models really, there wasn't anything special about the image. Like they weren't necessarily special to like 2D images. It's an architecture that can be expanded to do basically anything similar to this. You have to just have the right training data and just make sure that the regressions that you learn match the way that your bounding boxes are parameterized. Cool. That's actually it for today. That's what we did. We did all these things. Any questions?
So is the text labeled? So do we need to label the text?
Yeah. So the camera itself learns to infer depth through. I mean, I think, yeah. So like, how does the Connect do it? So we know how LiDAR does it. This is physics. It's like solving an inverse problem from the scanner, just like kind of any sort of DAR sensor does. But for the Connect, I'm not actually sure how it does it.
What was the question?
I can't. Is there like a model in there that's like learned depth, or is it just inferring it from? I mean, there must be a model in there that's collecting the depth.
A single way is just based on the reflections times the light speed.
Yeah, but I don't think that's how it works. Like that is a way it could work. Like there's a sensor for that.
Like to find the distance.
But I don't think that's how it works.
To find the distances, the Kinect.
How does the Connect do it?
Doesn't it have the 2 cameras, and then with the 2 cameras, if you put.
Oh yeah. So it's like binocular.
Yeah, it's the binocular. It just calculates the discrepancy between the two.
Yep. That's right. And it has a model for deciding the depth. That's right. Thanks. But yeah.
But that is not a neural network.
No, that's not a
That
neural
is
network. That's just like physics. Like that.
Yes.
It's just